Simple pendulum with string length L tied to a small ball is pulled tightly up and makes a 30-degree angle above the horizontal, as shown in the figure here. The ball is then released. What is the ball's velocity at the bottom or lowest point of the pendulum? So let's start by drawing a diagram for this. So we can actually divide this movement into two parts. The first part is simply going to be free fall, as it's just released from this 30-degree angle. So let's say that this is the string of length L. Here's the mass. This is the horizontal. And this is the 30-degree angle. Now, if you draw a dashed line here, this would make a right angle. And this part is where the ball is going to fall through, as you're just dropping it and it's entering free fall. It's not confined by the circle yet. So this is given by L times the sine of 30 degrees. Since this is just opposite of the 30-degree angle. This quantity is given by the length times the cosine of 30, which we won't really need right now. But after this, it's going to continue to free fall. So I'm going to erase that for now. We don't need this. So after reaching that 0 degree, or reaching the horizontal, it's going to keep free falling until the circle actually starts curving. So this again is L. This is also 30 degrees. So if we draw the circle as like going around here, there are 2 points in the circle that are going to touch the string at this point. These 2 points. So the mass is going to keep free falling until it reaches this point, which is 30 degrees below the horizontal. And this length is also given by L sine of 30. So this is for stage 1. So now let's go back over here and try to figure out the velocity when the ball is here. We need to figure out the velocity here. So we know that the gravitational potential energy is going to be converted into kinetic energy of the fall. So when the ball is held up, it has the kinetic energy that is equal to the mass times the gravitational acceleration times the height that it is held above the ground. In this case, it is the height above when it will start performing circular motion. And that is equal to the kinetic energy. So now let's plug some things in. So mg, and h is actually 2L sine 30. Since you have 2 of these, each of these length is L sine 30, and you have 2 of them. That's going to equal 1/2 mv squared, which is the equation for kinetic energy. Now the masses will cancel, and this becomes 2L sine 30, because simply becomes 2L times 1/2, because the sine of 30 degrees is simply 1/2. That is going to equal 1/2 v squared. The 1/2s cancel, so you're left with v squared equals 2L. Oops. There actually is the other thing, g. So can't forget about g. G2L half. So 1/2 v squared. These two cancel. So left with v squared equals 2gl. So v is equal to the square root of 2gl. So this will be the velocity after its free fall. And after that point, it will start performing circular motion. So I'm going to rewrite this over. So I'm going to erase this diagram since we can draw a new one for the second stage. So velocity after free fall is equal to the square root of 2 times the gravitational acceleration times the length L. Now for stage 2, this is going to be for when the ball has actually dropped past the horizontal. So this is our coordinate system. This is the 30-degree angle. And the ball is going to be here. So from then on, it's going to be following this circular path instead of simply free falling. So it's actually going to start following a circular path. And these two angles are complementary since this makes a right angle. So this is 60 degrees. So for the next 60 degrees, it's going to have to undergo circular motion. Again, this is length L. This is length L sine 30. So from this point on, when the mass starts undergoing circular motion, it's going to have a few more components. So first of all, it's going to have the velocity. That's going to be straight down since it just came out of free fall. All of that velocity is going down. It's going to have the tangential velocity, which is the velocity tangent to the circle, and it's going to have the radial velocity, which is the velocity that is actually going away from the circle, and the string will need to provide an impulse to get rid of this. What we're focusing on is actually the tangential velocity. So we know that the tangential velocity and the radial velocities are perpendicular. So this makes a right triangle. And the angle there is actually 30 degrees here. So we can say that the tangential velocity is equal to v times the cosine of 30 degrees, which is simply equal to the velocity times the square root of 3 over 2. So that's the tangential velocity. And now, again, we can use energy conservation to say that the potential energy over here, or the total mechanical energy actually, is going to be equal to the kinetic energy at the bottom. So by mechanical energy, I mean both the gravitational potential energy and the kinetic energy it initially has from the tangential velocity. So again, the radial velocity is going to be gone because the string will provide a centripetal force to reduce this to 0, so that the ball won't, or the mass won't actually escape this circular orbit. So from there, we can say this expression is for the gravitational potential energy. MgL, which is up here, minus L times the cosine of 60 degrees, which is this length here. So we need to subtract those two to figure out the gravitational potential energy. And then we're going to add the kinetic energy from the circular motion, the tangential component from the circular motion of the velocity that it already had when it was falling. I'm going to rewrite this a little smaller. MgL minus MgL times the cosine 60 degrees plus 1/2 mvt squared is equal to 1/2 mvv squared. And in this case, this is the kinetic energy at the bottom, and Vb is representing the velocity at the bottom. So we can go ahead and factor this whole part out. 1 minus the cosine of 60. 1 minus the cosine of 60 is actually 1 minus 1/2, since the cosine of 60 is 1/2. And going to 1/2 mv squared t squared equals 1/2 mvv squared. And we can cancel out the masses and then multiply both sides by 2 to get 2gl times 1/2 is 1 minus 1/2 plus vt squared is equal to vb squared, where vb is the velocity at the bottom. So now all we need to do is solve for vb, the velocity at the bottom. So vb squared, these two cancel each other out, so it's just simply gl plus the velocity of the tangential component of the velocity when it's undergoing circular motion squared. So if you recall, we figured out that it is equal to v times the square root of 3 over 2, where v is the square root of 2 times GL. So I'm going to make more space by squaring it. So we can say, from there, we can say tangential velocity squared is simply equal to v times the square root of 3 over 2. That's v squared, which is equal to v squared, 3v squared divided by 4. And now we can substitute the velocity that we calculated earlier back in. So this is equal to 3 times the square root of 2GL squared divided by 4, which is equal to 6GL divided by 4, which is equal to 3GL over 2. So that is what we get for the velocity of the tangential component squared. So I'm going to go ahead and plug that back in to get that velocity at the bottom is equal to GL plus 3GL over 2. And then now we just need to square root that. To square root. And GL plus 3GL is simply 5GL. And we're going to divide that by 2. And that our answer is going to be in meters per second. And this is the velocity at the lowest point of the pendulum.